Chapter 6, Momentum Analysis of Flow Systems. All right, class, today we're going to imagine you are standing at the back of a fire truck, holding a big water hose. When you turn on the water, you feel a push backward. That push is not magic, it's the power of momentum. In today's story, we will talk about how fluids like water and air can push, pull, and twist things just by moving using something called momentum analysis. You've all played with toy cars, right? When you push a car, it speeds up, and when you stop pushing, it slows down. That's called Newton's laws. The first law says things keep moving or staying still unless something pushes or pulls on them. The second law says how much something speeds up depends on how hard you push and how heavy it is. The third law says every time you push on something, it pushes back on you just as hard. In fluids, we use these laws to figure out how much force water or air puts on pipes, turbines, rockets, or even our bodies. Instead of looking at every water droplet, we imagine a big box around part of the water flow. That box is called a control volume. It helps us count how much fluid enters, leaves, and pushes inside the box. Sometimes the box doesn't move, like water in a pipe. Sometimes it moves with the flow, like air around a flying airplane. And sometimes it stretches or shrinks, like air inside a pumping balloon. Now, we count forces in two ways. First, the body forces, like gravity pulling everything downward, like why water flows downhill. Second, surface forces, like pressure pushing on pipe walls and friction slowing things down. When we count forces inside our box, we ignore what's happening deep inside unless we slice through it. We focus on what's happening on the outside of the box. Engineers like to be smart, so we choose boxes that make counting easy. Like when we figure out how much force holds a faucet in place, we can cut through the bolts, count the pressure at the water entrance, and skip worrying about friction inside the pipe. There's a magic equation called the momentum equation. It says the total push on our box is equal to how fast fluid momentum changes inside plus how much momentum flows in and out. Most times, for steady flow, the inside momentum doesn't change, so we only need to care about what comes in and out. We use vector arrows, called vectors, to show direction because it matters if the water is going forward or backward. Sometimes we use average speed to make calculations easier, but because not all water flows at the same speed, we use a little helper number called beta. It corrects our answer to be more precise. When the flow is smooth, beta is bigger, like in slow, smooth water in a pipe. In wild, rough flows, beta is close to 1, meaning averages are good enough. In fun examples, we see things like water jets pushing on plates, elbows turning water in pipes, and rockets making spaceships slow down. When the water changes direction, it pushes harder, like when you throw a ball and hit a wall, it bounces back and pushes you more. Rockets get pushed by the gas blasting out, and windmills spin because wind pushes their blades. So, class, fluids are like invisible hands. They push, pull, and even spin things just by moving. Engineers use these ideas to build safe bridges, strong airplanes, fast rockets, and even quiet water taps. Every time you feel a push from water or air, you are experiencing momentum in action.